Hi, and welcome to USMA Orgo. We're going to talk about Chapter 4, which is Nomenclature and Conformation of Alkanes and Cycloalkanes. So first, there's a lot of relevance to cycloalkanes and alkanes to our world and what we use every day. First being petroleum, and if you look at the figure here, you can see that alkanes are used from anywhere from natural gas all the way down to waxes and asphalt and tar. So in our modern world, we use petroleum a lot, and that's all primarily alkanes. So now naming alkanes is pretty important because you'll be using this for the rest of the time you're in organic chemistry. And there's a lot of sections in the book that outline how to do the naming. You have just naming branch-chain alkanes, very important. Alkyl halides is on page 151, alcohols page 152, cyclohexanes on page 153, bicyclic cycloalkanes, alkenes and alkynes, again, all very important ways of naming. Another thing that's really important is that you understand this is half of a chart that's in your book, but memorizing methane through decane and what they mean will help you with naming. And then finally, and last note on naming, although you need to spend a lot of time on it with homework and understanding, is this idea of when you, over here, when you have methane, it becomes, as a substituent, you make it a methyl group. Ethane, you can see, becomes an ethyl group, propyl and butyl, and so on. Next thing is physical properties. I'm not going to get into a lot here, but you have to understand that the shape of a molecule and what's connected to it and how it's connected give rise to a lot of the physical properties. So take a look at it in your book, do a lot of reading on how the shape changes the boiling point, the melting point, the density, and the solubility. All very important when you're trying to consider what alkanes to use for things and how you might be able to modify them to get a more favorable physical property. Next is sigma bond rotation. So when you have a sigma bond between two carbons, as you can see here, there is free rotation around that sigma bond, which means that those hydrogens can take on different conformations as you spin those two carbons around the sigma bond. And for example, down the lower left, you'll see that in just a simple compound, you can have a situation that's in lower in energy, if you see this energy diagram here, lower energy where they're staggered. So that means that all the hydrogens are separate as far apart as they can possibly be. And then the most high energy conformation would be here, where you have them eclipse, where the hydrogens are right in front of each other. And then again, if you rotate it one more time, you'll get down to the staggered. Now that becomes a little bit more difficult when you have bigger molecules. So when you have bigger molecules, you have not just hydrogens on the carbons to deal with, you have other groups. So for example here, you see that there's methyl groups that you have to contend with. So now there's a lot of different conformations you can end up having, where you have new terms called the anti and gauche conformations, and then again the eclipse and staggered that we had before. But now when you talk about anti, that's when these groups are as far apart as they possibly can be, so that's a lower energy. And higher energy in the eclipse is this, where they're right on top of each other, or right in front of each other. And then there's other conformations, gauche, where they're next to each other but not overlapping with each other. So as you rotate through the different rotations of the bond, you can see there's different energies, and those kind of help us predict how a conformation or how a molecule might exist, which would be the lowest energy state it possibly can be in. So then we can then translate that to the stability of cycloalkanes. So when you have a cycloalkane, there's things like angle and torsional strain, which you have to deal with. You can take a look at the definitions in the book. The book also gives you some instructions on page 172 on how to draw chair conformations. And then, as you see down here, again, we have an energy diagram which shows you the different conformations and which ones are more stable. So the chair is the most stable conformation. But if you get up to the half chair, that's the most unstable conformation because it has the highest relative energy, which is in part because of these interactions, the 1,3 diaxial interactions that you'll see. Also, you can talk about different conformations like cis and trans conformations because of the 1,4 conformations. So take a look at that in the book, do a lot of reading on that because it's an important concept to understand how 1,3 diaxial interactions happen and how you might name something or explain something based off 1,4 conformations. So now hydrogenation of alkenes and alkynes. So we can now start talking about reactions where we convert from one type of molecule to another. In this case, we use an alkene. We add hydrogen across the double bond, and we get an alkane. So that happens by using some sort of metal and a solvent, and then usually under pressure. Another example, as you can see here to the right, is when we have an alkyne where you have to use twice as many hydrogens, but again, you can saturate it completely with this type of reagent. And then below here, there are some specific examples where they're using nickel as the metal. The ethanol is your solvent, and proton source is some kind of, actually the proton source is hydrogen gas, and then we use a higher pressure to make that happen. Same thing with the other two examples. They're showing you different metals to be used, so palladium in this case. So on page 182, there's several rules for calculating index of hydrogen deficiency. This is going to be very important throughout the course, specifically when we're looking at spectra and things of that nature. So go through the steps on 182 and pay attention to how to do this and how different substituents make an effect on the index of hydrogen deficiency and what constitutes a hydrogen deficiency and how you can predict that. Finally, there's a summary on page 190, as usual, that does a good job at kind of laying out the different parts of the chapter that you're supposed to learn, from all the naming, and then all the different kind of conformations, and then how we can talk about those here. And we go down to the inland projections, which are important and to learn about, and then the different chair conformations as well. So, hope you have a good day. That's it for chapter 4. See you soon.